Welcome! In this video, I'll show you how to solve problem 9.1 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem states the following. It says, a hydrogen atom is placed in a time-dependent electric field, which is E as a function of time in the K direction. Calculate all four matrix elements H prime Ij, and just keep in mind, H prime Ij, as we saw in the previous video, is simply shorthand notation for the inner product of state psi A, H prime state psi J. Of the perturbation where H prime is minus E times big E times Z. Okay, so this is in the Z direction, of course. And well, we want to do it between the ground state, n equals 1, and the quadruply degenerate first excited states, n equal 2. Okay, so there's going to be quite a few states to work with. And we want to show that H prime II is equal to 0. So this is what I mentioned before. Whenever it's going to be very common that for all of our states, we have that H prime of AA, which is the name that we used in the other video, or H prime II, more in general, it's going to end up being 0, which will mean that the simplification that we used when we simplified the formula at the end of the previous video is going to be valid. So that's going to be true for all 5 states. Note, there's only one integral to be done here if you exploit oddness with respect to Z. As a result, only one of the n equal 2 states is accessible from the ground state by a perturbation of this form, and therefore the system functions as a two-level configuration, which is what we have been working with so far, assuming transitions to higher excited states can be ignored. Okay, so let's begin working with this, and we will then begin interpreting. So what we want to do here is we want to find these elements H prime II, H prime Ij, because they are what give us the coefficients Ca and Cb that we saw in the previous video, right? So in this part, we don't really want, they are not asking us to find the coefficients themselves, simply the elements, but they themselves kind of give us the coefficients, so we are working towards that. Now, let's begin, for example. Well, first of all, I just wrote down all of the relevant formulas here for our wave functions, so we don't have to worry about them later. So let's begin, for example, for psi, let's say 1, 0, 0, H prime, psi 1, 0, 0. So first, let's begin only by taking the inner product with itself. This thing right here means that we take the integral over all of space, and then we have what is inside. So we will have this thing squared. So we have 1 over pi a cubed e to the minus 2r over a. And then we have our perturbation, which is minus e ez. So we have minus e z, and we have to choose our coordinates. Now, because we already have z here, and because they kind of give us the hint that we will be exploiting oddness in z, we should probably go for a Cartesian coordinate, even though it's kind of weird because we have spherical symmetry. But just to make sure that we see this particular property, we will use Cartesian coordinates for now. So that means dx, dy, dz, and we integrate 3 times from minus infinity, Actually, I'm just going to write it like this. So big minus infinity to big infinity, right? For all 3 integrals. Okay, so that is what we want to integrate here. Now, the question is, well, of course, integrating this in Cartesian coordinates is a nightmare, but we wish to see if this is even or odd. So let's begin by taking a look at this. Well, there is no z in here, so you'd be inclined to think, oh well, then this is even, right? If there is no z, then that function of z is the same as that function of minus z. But you would be correct, but for the wrong reasons. So you have to keep in mind, in spherical coordinates, r is simply x squared plus y squared plus z squared, and the square root of all of that. So this exponential right there is actually 2 square root of x squared plus y squared plus z squared. Now, of course, z squared is even, so this thing does end up being even, but it would have been a lucky guess if you didn't know this. So that means that this part is even, and this part is odd. So an even function times an odd function is going to be odd. And why is that relevant? Because we are integrating from minus infinity to infinity. So that means we are integrating a symmetric interval, right? Or rather an odd function in a symmetric interval. So everything that is smaller than 0 is going to cancel out everything that is greater than 0, right? Just for example, right, if you evaluate this at 1, as z equal 1, it's going to be the same as minus evaluating this at z at minus 1, right? So if you add them together, they cancel out. That's my point. I think I didn't say it correctly, but I hope you know what I mean. Okay. So my point is that this thing is 0. You don't need to do any sort of integration. And this exact thing is going to happen all the time. So for example, let's now take a look at this part. So we will have to integrate, of course, the modulus squared of our wave function to 0, 0, right? And then we multiply by h prime. That is what goes inside of the integral, right? So this is what we need to analyze. If this is odd, then we get 0. If this is not odd, then we will have to integrate. So let's see, in this case, psi 2, 0, 0, we have these constants, which are irrelevant for now, right? If this is going to be 0 anyways, we don't care about those constants. So we have this part there, which we'll have to square. So we get 1 minus 2 times r, so we get r over a, plus r squared over 4a squared. And then we have e to the minus r over a, because we get this thing squared, which is 2r over 2a. And then we multiply all of this by minus EEZ. You could have just ignored this because they don't change the oddness or evenness. Either way, take a look at this. R is even, right? We can see it right there. It is even, it is z squared. R squared is also even. This part is also even. So we have all of this, which is even, and this, which is odd. So that means that if we take the integral, then we get that h prime of 1, 0, 0, sorry, no, we are doing 2, 0, 0 now. So 2, 0, 0, 2, 0, 0, this is 0. Okay, so that is important to note. And you can see that we're going to get a lot of zeros here. And that is why, again, in the other video, I was mentioning that we can often assume that that part is 0. Now let's go for state 2, 1, 0, which is this one. So again, the constants will not change the result. So if we take a look at the modulus squared times h prime, this time we get r times cosine theta. This is squared, so r squared cosine theta squared. I'm going to ignore this 1 over a because it's a constant. And then we have e to the minus 2r over a, and all of this times z. So there's a few ways to look at this, but you have to be careful because here we have cosine theta. And you know that you can relate the angle theta to some of the Cartesian coordinates. So you have to be a little bit careful. Here, you should keep in mind that z is equal to r cosine theta. So that means that this thing here is z squared. So all of this is once again even, right? Z squared is even, r is even because it has a z squared, and this part is odd, right? This z, of course, comes from the perturbation minus EEZ. So this entire thing will give us 0 when we integrate. So this also will be 0. So maybe let's write it down here. So h prime of 2, 1, 0, 2, 1, 0, this is also 0. Okay, so now the final one that we have to take a look at least the final one of the form, you know, h prime I, will be these two. So there's 2 here, right? There it might be a little bit more difficult. So let's begin by taking a look at what we have there. So here we have this r sine theta, theta e to the plus or minus I phi. So let me now zoom in, and we can work with this a little bit because, again, we know how r depends on z, but how does theta, how does phi depend on z? Is it even? Is it odd? it's a bit hard to see. So let's try to transform this. Now, from Euler's formula, we know, of course, how we can rewrite this complex exponential. We know that it is cosine of phi plus or minus I sine of phi. But what we have here, so if we multiply, of course, we get r sine theta cosine phi plus or minus I r sine theta sine phi. And this is precisely, so this thing right there, r sine theta cosine phi, that is x, and this thing right there is y. So r sine theta e to the plus minus I phi, that is x plus I y. So that is very important, because now when we take a look at this, so let's see, we want modulus squared of psi of 2, 1 plus or minus 1, right? We can do them at the same time. So that thing squared times our perturbation. Okay, so from here, again, we don't need to take the constants into account. We have r sine theta times the exponent. We know all of that is x plus iy squared. So there is an x and y dependence, but there is no z dependence there. And then we have e to the minus r over 2a. But this thing right there is even. So all of this is even in z. It doesn't matter if it isn't in x or y, because we have three integrals, right? If one of them is 0, then the product is going to be 0, so it doesn't matter. Okay, so we have that part, and of course then we still have this minus EEZ. So all of this is even, this part is odd, so the end result is odd, so this entire integral will be 0, right? The integral in z will be 0, so h prime of 2, 1 plus or minus 1 with 2, 1 plus or minus 1 will be 0. So there we go. So now we showed that all 5 states give us that this part is 0. Now we have to begin working with the cross ones, right? So basically, we want to go from state psi 1, 0, 0 to psi 2, 0 or 2, 1 or 2, 1 minus 1, right? So we want to deal with transitions. So if we go from this to there or this to there or, you know, some other one, we want to take a look at which one of those will not be 0. Okay, so we already used this part. I'm going to get rid of it. So let's begin by taking a look at psi 1, 0. So basically, we will begin with h prime of 1, 0, 0 and 2, 0, 0, right? So we'll combine these two. So when we do that, so I'm going to do this in more detail, and then we'll do the other ones quicker, like we did before. So here we would have this integral over all of space, so minus infinity to infinity in Cartesian coordinates, 1 over square root of pi a cubed, 1 over square root of 8 pi a cubed, and then we have e to the minus r over a, we have e to the minus r over 2a, and 1 minus r over 2a, and we still have the perturbation, so we get minus e z and dx dy dz. So what do we have here? Well, notice that this thing was already even, so of course all that corresponds to it is also even. This part, which corresponds to psi 2, 0, 0, is also even, so we have even times odd. So this entire thing is also odd, which means that the integral in z will be 0. Okay? And that is, of course, because, well, again, this is even, this is even, this is even, that is odd. And the integral of an odd function in a symmetric interval is 0, right? So integrating over z. Next, we could go for h prime 1, 0, 0 and 2, 1, 0. Now, what would happen here? Well, in that case, we would have, this is even, and here we have r cosine theta, which is z. So this part is actually odd. So this integral, if we integrate these two, right, this is not necessarily 0. So we will leave it in standby for now and solve it later. So let's continue with another one while we figure it out. So for example, psi 1, 0, 0 with, actually let's use the same notation. So I mean h prime of 1, 0, 0 with 2, 1, plus or minus 1, for example. So in this case, well, what do we have? Let's see, so we have even function here, and this entire thing is x plus iy. So this is also even. So we have even function times an even function times the odd perturbation. So this will also be 0. So no need to go for it. So every single combination, every possible transition, right, is 0, except for, or at least this might be 0, we don't know, but at least we can't say that it's 0 for now. So this is the only integral that may not be 0. Let's see. So let's actually plug it in. However, notice that since we actually have to solve the integral, I will not really use Cartesian coordinates anymore. I was only using them to see evenness or oddness, but using them to actually integrate is really, that's not good. It's going to be very, very difficult. So let's plug everything in. So we have integral from 0 to infinity, that's r, 0 to pi, 0 to 2 pi, and then we have, well, the constants, so square root pi a cubed, e to the minus r over a, and then we have 2, 1, 0, so we get 1 over 32 pi a cubed, and then we have, let's see, we have r cosine theta. Now we don't want to write it as z anymore, so we leave it like this. We divide by a, and then we have e to the minus r, and I'm just now noticing that I must have copied this wrong. For the state 210, it is minus r over 2a, so be careful there. It doesn't change anything that's happened, thankfully, but it is a typo that I had, so be very careful. So it is minus r over 2a. And then we still have, of course, the perturbation itself, which is minus e times z, but z is r cosine theta. And then, of course, since we're integrating in spherical coordinates, we still have to add r squared sine theta. And then, of course, dr, d theta, d phi. So this is what we have to integrate. So maybe now let's separate everything. So there's a few things. I'm just going to put all the constants outside. So let's see. We have a cubed times a cubed inside of a square root. So that will be a cubed squared. So we end up with 1 over a to the 4th power. We can also take out a pi from the square root, and I think that is it. So we still have 1 over the square root of 32. Then we have the r integral, so we go from 0 to r. Oh, and we have, of course, the minus e, which I'll put somewhere here. So minus e. We go from 0 to infinity of e to the minus r over a minus r over 2a. Here we can simply add them together, of course, take common denominator. We write this as 2r over 2a, so we get minus 3r over 2a. So minus 3r over 2a. All right. What do we have next? So we have used this and this. Then we have, let's see, r cosine, so we get r squared cosine squared of theta. I guess I could put the cosine elsewhere. So we have r squared and another r squared. So we end up with r to the 4th. And that's every single r, right? Yes, dr. Then we have integral from 0 to pi. And now we have everything with theta. So we have sine of theta, cosine squared of theta d theta, and then we have the integral of phi, but there is no dependence on phi, so that one is easy. Okay, amazing. So now we have to solve each one of those. Now let's call them I1, I2, and well, there's no need, but I'll call it I3. Now we have solved each one of these many times before. So I1, this one is solved by using integration by parts many times. You would say, okay, u is equal to r to the 4th, du is equal to 4r cubed, and then you have dv, which is e to the minus 3r over 2a dr, and v is going to be 2a over 3 e to the minus 3r over 2a. And from here, you have, of course, this product, which will be 0, because you have to multiply these two, evaluate it between 0 and infinity. And at 0, this part is 0. At infinity, this part is 0. So that part is always 0. So you end up with minus 4 times the integral from 0 to infinity of r cubed times e to the minus 3r to a dr times 2a over 3. So you get the same thing as before, but with 4 and with this. So in the end, you have to use integration by parts again here. And that time when you do it, you get a 3. So you get 4 times 3. And then you get another one of these and you get this thing squared. And then you have to do it again, but this time it is squared. And then you get times 2. And then you get times 1, right? And you get more and more of those. So in the end, what you end up with is going to be, and I'm actually going to link you guys in the description a video where I do this explicitly, because we have to solve this so often that I just want to have the link there and just reference you. This is how you solve it, and it's going to be easier. So the point is that when we have an integral like this, something like, actually I'm just going to show you what it is here right away. So in this particular case, what we do to solve it, right, just using the basically recursion that we saw, is that we say, okay, let's use a change of variables here, because this dr, we don't have the r alone. So we say u is just 3r over 2a, which means that du is 3dr over 2a, which means that dr, this is 2a over 3 du. So we can plug this into the integral. The limits of integration are unchanged, right? When r is 0, u is 0. When r is infinity, u is infinity, so it doesn't change. And we have e to the minus u, and then we have r, which is, from here we see that r is 2au divided by 3, and this is to the 4th power du, or rather dr, but dr is du times 2a over 3. So from here, we see that this thing is 2a over 3 to the 5th power times the integral from 0 to infinity of e to the minus u du, and of course u to the 4th power, And that integral is, like we saw, simply 4 factorial, right? You get 4 times 3 times 2 times 1, and the limits always cancel out. So this is 2a over 3 to the 5th power times 4 factorial. So there we go. Again, I will put a link in the description where I solved this like very generally and just show you how to solve it by integration by parts or by using the formula, just in case you have never seen this before. Okay, then we have integral 2. Now, integral 2 we solve by substitution. We use u is equal to cosine of theta, and thus du is equal to minus sine of theta d theta, because that way, when we integrate from 0 to pi, well, actually the limits are changed now. So if theta is 0, we get 1. If theta is pi, we get minus 1. Okay, so we have cosine squared, which is u squared, and sine theta d theta, that is minus du. So that means that, we went from an integral that is quite difficult to this one. So that is why we use that substitution. And this integral is trivial, right? It is u cubed over 3 with a minus sign. And we evaluate between 1 and minus 1. So this is minus. Evaluated at minus 1, we get minus 1/3, minus evaluated at 1, which is 1/3. So this thing is 2/3, right? The minus signs cancel out. And finally, that other integral, that is simply 2 pi. So this entire thing is minus e divided by pi a to the 4th power square root of 32. And then we have times 2a over 3 to the 5th power times 4 factorial and times 2/3 from the other integral. So times 2/3 times 2 pi. And there we go. So there we included everything. So that is what we have well, the pi's will cancel out. Then we have a to the 5th power and a to the 4th power. So this and this, it partially cancels out. So we end up with minus e a. Now we don't, well, we know the value of small e. We don't know the value of big E. We don't really need to plug it in. We're just going to leave it like that. And all the other constants, so we have 2 to the 5th power times 2 times 2, this square root of 32, 3 to the 5th power, 3. All of that simply gives us 0.7449. So that is our result. Okay, so that is the value of that matrix element. And this also tells us, of course, that the only possible transition, and this is kind of where the interpretation comes in, right? This is what they were saying here. The only state in n equal 2 that is accessible from the ground state by a perturbation of this form, right? So if you use this sort of a perturbation, we will soon see what this means, but for now, we will just leave it mathematically. Like this, the only state that is accessible is 2, 1, 0. So if you have something in the ground state, you can only, by using this perturbation, take it to state 2, 1, 0. The other ones, they are not possible now. There could be higher excited state possibilities, and you could do the same procedure for them, but in this case, we didn't have to take them into account. So I hope that this video was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe even checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.